Okay, so in this problem today, we're going to be talking about carts attached by strings and finding the tension between the two carts. And so, what would you like to do? As in, how would you go about solving these problems? What's the first thing that you would notice or write down or think about? Yeah, we could do F equals MA. So when I do F equals MA, I could look at the individual cart 2, the individual cart 1, but F equals MA is our only force equation. So why don't we look at the big picture of everything? Because that 8 newtons is pulling on how many of the carts? Both of them, right? And so by looking at the combined cart 1, by looking at the combined cart 1 and 2, we have the fact that the net force equals MA, which is how it will move in the X direction, right? We also have its up and down forces. Do we care about gravity if it's on wheels and on a surface and we're looking for how it moves? Do we care about how it sits on the surface? Because gravity will be opposed by the surface. Gravity will have its matching normal force. Are those the equal and opposite forces? Even though they are equal in value and opposite in direction, you have a gravity pulling down, which means somewhere else in the universe you have a gravity pulling up. You have a normal force, which is the contact force of the cart sitting on the ground. So also you have the ground pushing up on the carts. That's what we're talking about. You have the carts pushing down on the ground in return. Okay? And so this is not the equal and opposite forces, but we are not worried about the ups nor the downs. So if we combine 1 and 2 and look at the big picture, the net force, what's the net force on all of the objects? 8 will equal, what's the mass? M1 plus M2. So that's 2. So 8 equals 2 times A. What does your A equal? A equals 4 meters per second squared. And what if we just look at the carts individually? Because we have how it moves. What happens with cart 2? It also moves at 4 meters per second. Well, let's look at all the forces that make that happen. So we've got gravity. So here's my free body diagram of, so these are my free body diagrams of cart 2. We have a downward arrow for gravity. We've got an upward arrow for normal. And what else do we have? T pulling it forward. Okay. For cart 1, what do we have? We have gravity. We have normal. What else does cart 1 have? Tension force. Which way does tension go? To the left. And then we also have the forward force applied to the right. So, what if I'm looking at cart 2? What happens if I'm looking at cart 2? What's the math behind it? I'm going to write it on this side. If I'm worried about cart 2, I have that the net force in the X direction equals tension, right? That's the only arrow moving left and right on this box. Tension. So then tension equals, well, the net force equals ma, right? So the net force on cart 2 is ma. The net force is also tension. What's the mass? And what's the A? Acceleration. 4. Okay. So the net force on box 2, which is the tension, equals 6. T equals 6, which is also the net force. 6 newtons. All right. How does that make sense for cart 1? What did we have going on in cart 1? The net force in the x direction equals force applied minus tension. And also you could say that the net force of x equals ma. How does that make sense? What's this top part? What's the force applied? 8. And then minus 6. What's that? 2. What's the ma of the first box? M is 0.5 times 4. Huh. What should that equal? 2. So it's kind of convenient that we can even check our own work because it works itself in a circle. All we're really doing is taking the 8 newtons of force and really distributing it across 2 kilograms of mass, but a quarter of that is in cart 1 and 3/4 of that mass is in cart 2. And so the acceleration, which is 4 meters per second, both of these carts to move at that acceleration has to distribute that force across both of those carts. All right. Guys, the logic portion is not hard. When I did this the first time in the morning, a lot of times it has a lot less work. That's why I don't record during first period. But then it's the work that we actually grade. So first period, they have to make it up afterwards. We go back and we show all our work. Okay? The concept isn't hard. And the first thing we did was figure out the acceleration. And then we just figured out, okay, if they both accelerate like that, how does it move? Oh, yeah, the tension's pulling on that cart too. That's it. Okay? All right. Number 2. What do we see? Let's look at the whole system first. So what do you see in the system? We have our master equation, F equals ma. The net force equals all 3 masses, right? Have to be accelerated with that net force. So what is the net force? What's the only force outside of this? 12 newtons. Outside the boxes in the system is 12 newtons. Equals, what's the masses added together? Yeah, 2 plus 3 plus 1 is 6 kilograms. So A, yes, A equals 2 newtons per kilogram? Yes. Same unit as newtons per kilogram. So how do we find T3? What cart do you want to look at for T3? Cart 3 only? If I looked at cart 3 only, I could worry about gravity, I could worry about the normal force, but really, what's the only force that's left to be reckoned with? The net force in the x direction is equal to tension 3. And the net force in the x direction is also equal to MA. Right? Really what we're saying is the net force is equal to MA. And tension is the only force that's providing that net force. Mass. 2. Acceleration. 2. So T3 equals 4. 4 what? Newtons. Why don't I just write that right here on my picture? What does that mean that's happening on cart 2? That it's getting held back by 4 newtons. So how do you want to find T1? I mean T2. What cart do you need to look at for T2? Cart 2. Okay, so here's cart 2. What kind of forces do I have to worry about on cart 2? You said T2 and T3? All right. So if I'm worried about T2 and T3, that means I'm saying that the net force in the x direction is equal to T2 minus T3. Good. And also I could say the net force is equal to MA. So if MA is equal to T2 minus T3, wait, what's the mass of cart 2? 3. What's the acceleration of cart 2? 2. What's the force of T3? Right. So I've got, what number is this? What's 3 times 2? Plus 4, right? I move this over? Yeah. T2 equals 10. Now, the other way that you can think about this is, how much does T2 have to pull behind it? How much does T2 have to pull behind it? How many carts? How many carts are behind T2? 2 of the carts. Both carts. You need both carts. You need to pull cart 2 and cart 3 with this force. So a total of 10 kilograms is pulled forward with 2 meters per second squared to get you that 10 newtons of force. Does that make sense too? That's another way we could do it. Then what's pulling all of them together? We already said that. We've got 12 newtons of force pulling all 3 of them. We've got 10 newtons of force pulling these last 2, and 4 newtons of force pulling the last one. It's kind of like this. Let me pick a different color. It's kind of like we got a guy here, and if instead of tension, you were trying to hold the rest of the train, it's way easier to hold the last train cart than the whole entire train. Right? Does that kind of make sense? If you're the person who's like, man, this train's moving and you don't want the train to separate, it's way easier to be the last coupler than the first one. Does that make sense? This person would be responsible for helping move the whole entire train behind it, as opposed to just the caboose. All right, last one. 2 crates, masses 12 and 20, are pushed across the smooth surface. Tell me what to do. F equals ma. Guys, if on the test or quiz you don't start with this equation, then you're going to lose a point. So if you didn't start with that equation, just write it down like you did. All right. What else are you going to do? What else do we need? The force. Wait, do we have the force? Equals both of the masses, right? M1 plus M2 times A. Oh, wait, we have all of those parts, though. 20 plus 12 times 1.75. Is that what it says in the words? And that's 56. 32 times 1 3/4. 56. Force equals 56 newtons. What are you going to do with this 56 newtons? How many boxes do you need to push with this 56 newtons? Okay, so that's the force applied to the crates. What's the between the crates, though? So how am I going to measure what box 1 pushes on box 2 and what box 2 pushes on box 1? How am I going to measure that interaction?
It could be like F net minus FC is equal to MA.
Yeah, you could do that. What else could you do? Which box could we zoom in on? How many forces are acting on box 1? Technically 4. You have the up and down, but yeah. I get what you mean. You have a forwards and backwards force. Is that the 2 you're talking about? Okay, so the force on box 2. How many forces act on box 2 though? Okay. I know what you mean by saying 1. There's 1 net force. We do have gravity and normal force pushing up. So the force on box 2 is equal to the mass of box 2 times the acceleration of box 2. And we know that it accelerates at 1.75. And we know that the mass is 12. So we know that the force on box 2 is... And this is a net force, huh? The net force on box 2 is... Oh, I can't do that in my head right now. That's 12 3/4 of 12, so that's 21. Yeah. 12 plus 9 is 21. And I guess my question to you is, does it make sense that this is 21 newtons of force if this force is 56 newtons of force? What is happening to box 1?
Moving to the right.
So the force is on box 1. Not only is it moving to the right, but it's getting held back by 21 newtons of force. Does that make sense for box 1?
Yes.
Why? What else does that... So what's the net force? The net force on box 1 equals... The 56 is the force applied. And then we also have working against it, not tension. This is actually the normal force, right? It's a contact force of surfaces. And so you said that it's 56 minus 21, 35 newtons. What else is 35 newtons? What else matches this and should match this? F equals MA of just 1. Yeah. Is it correct? 20 times 1.75 is definitely 35. Cool. So what's crazy about these problems is that they always check themselves. If you notice, they lead into a circle where you can see, and as long as you look at the whole picture, and then you look at the individual items, you can check the forces between them. Just make sure that at one time you're looking at the system, at another time you're looking at the individual parts. And you can even think of everything behind that part if you wanted to, like the system of cart 2 and 3. Don't particularly find it useful to look at the system of cart 1 and 2 necessarily, but this part isn't too bad. Tomorrow, we talk about how that happens if we go up and down and then tie them together.